Mars, Bringer of War, from a suite of music that he wrote about the different planets. Very appropriate today to have that song playing, since we're going to talk about the orbit of Mars and how that was used by Johannes Kepler to derive his laws of planetary motion. So let us just quickly review where we left off yesterday. We were talking about the two different models of planetary motion, the Ptolemaic model or the geocentric model, and the Copernican model or the heliocentric model. And there's more to it, as we explained yesterday, than simply saying that what Ptolemy said, the Earth is at the center of the solar system or the planetary system, and Copernicus said the sun was at the center, because they both had detailed explanations. It was a very detailed model for both of them that would allow astronomers to predict planetary positions with a pretty high degree of precision. I think I said yesterday, I think I needed to clarify a little bit before I move on. Here this properly says that the Ptolemaic model agrees with planetary data almost as well as the Copernican model. Now, it's been debated over the years whether one was really better than the other by that big of a factor. When you consider everything as far as planetary data goes, the Copernican model is slightly better than the Ptolemaic model. But neither of them were perfect, and nor were either of them free of complications. As I said yesterday, the Copernican model required us to use things like epicycles, just like the Ptolemaic model did. So that's where it lay. And as I said yesterday, a contemporary of, really two contemporaries of Galileo, became involved in this debate. One of them, not as famous as perhaps Johannes Kepler, but certainly very important to the history of astronomy. His name was Tycho Brahe. And Tycho Brahe, he was born to a noble Danish family. At one time he owned his own island. Tycho Brahe decided at a very young age that he wanted to be an observational astronomer. In fact, he had a kind of a strange life to begin with. His uncle adopted him when he was 2 years old without telling the parents. Somehow he came to live with the uncle's family, and so the uncle decided to go ahead and adopt him. He studied law at first, and he discovered the other typical subject of the day. But he had this enormous interest in astronomy. And so in 1560, so he was born in 1546, so 1560, that would make him, 14 years old? He observed this eclipse. Actually, he made this statement after the eclipse. The eclipse was in 1560, but in 1563, when he was 17 years old, he made this statement: what is needed is a long-term project with the aim of mapping the heavens, conducted from a single location over a period of several years. So he had observed this eclipse, and he became so interested in astronomy as a result of it that he said, when he was age 17, that's going to be my life's work. I am going to observe the positions of things in the heavens. He had an artificial nose. He actually lost part of his nose in a duel. As I understand it, the duel was with another mathematician about a math formula, supposedly. He was one of the richest people in Denmark. He owned perhaps 1% of the wealth of the country. And he built this observatory on this private island that he owned, the island of Sven. The observatory was known as Uraniborg. And it was there he did exactly what he set out to do when he was 17 years old. He started to make this catalog of the heavens. Well, eventually, he was actually induced to move to Prague. That is where the Holy Roman Emperor lived at the time. And so he became the emperor's astronomer. They actually called him the imperial mathematician. But what they were basically asked to do was to make horoscopes, to make astrological predictions. Now, at the time, most astronomers doubted the efficacy of horoscopes, but that kind of paid the bills, and so they were willing to do it. But he took his massive amounts of data with him from his observatory on Uraniborg and made new observations. He's considered to be probably the best naked eye astronomer in history. He made such detailed observations. And the instruments, they didn't have telescopes. So naked eye astronomy, they did have sighting instruments, various types, very, very fancy versions of an astrolabe that I showed you the other day, something like that, where you could use it to sight things in the heavens. But that's what it was. It was just looking very patiently at the heavens and recording down what you saw. Now he was quite a famous social maven, I suppose, however you want to say it, and that may have been part of his undoing. He was had a whole entourage of people around him, and he loved to throw these lavish parties. He had a pet elk that was around. But anyway, he was supposedly at a banquet, and it was not a banquet that he was giving, so he was not the host there. And in those days, it was considered to be quite rude to get up and leave the table before the host did. Well, as the story traditionally went, he stayed at this table, and the host was not getting up, and he had consumed a vast quantity of wine, and supposedly the story used to go that his bladder burst, and that's what eventually resulted in his death. Now, modern physicians will say that just can't happen. You're going to lose control of your bodily functions long before that happens. However, there is some evidence that he may have contracted a bladder infection and tried to cure it using the methods of the day, which often involve things like mercury, which he may have died from poisoning from whatever it was that led to him needing to cure some kind of infection. So anyway, whatever it was, whether a result of trying to use alchemy to try to treat his infection, he died on October 24th in 1601. Now, his assistant at the time was Johannes Kepler, and we're going to show you in just a few minutes what the use that Johannes Kepler did put to Tycho Brahe's observations. I want to say a couple other things about Tycho Brahe's observations to astronomy. He gave us the word nova. He had a publication he wrote called De Stella Nova, Latin for about the new star, and he was one of these people that observed a new star appearing in the heavens. That's important because, as we said the other day, things in the heavens are supposed to be permanent and immutable and never changing, and yet here we have this new star forming. As we know today, a nova is an exploding star, a star that exploded, so maybe a star that was too dim to be visible from the Earth now suddenly is visible as a bright spot in the sky. And he also had the best model of planetary motion at the time of Galileo. His model was actually a hybrid system of the geocentric system and the heliocentric system. The geocentric system, what he did is he put all of the other planets were in orbit around the sun, but the sun orbited around the Earth. And in so doing, he was able to get a model that actually had a better agreement with the planetary data than either the Copernican system or the Ptolemaic system. But as I said, his most important contribution to astronomy was these really, really precise observations of the positions of the planets in the sky. So when he passed away, Kepler, his assistant, came into possession of his notebooks. And as I said, Kepler was going to make enormous use of these notebooks. Let's talk a little bit about Kepler first. He saw a comet in 1577 and wrote about it. And he was born in 1571, so okay, he's 6 years old and he's already watching comets, right? And he observed a lunar eclipse in 1580. He was originally going to study to be a pastor. He was Protestant, but he was dissuaded from that, so he eventually decided that he was going to study mathematics. And in those days, astronomy was kind of considered to be a branch of mathematics. He taught at a school in Austria for a while. And then eventually he got the attention of the Holy Roman Emperor, and so he went to work with Tycho Brahe in Prague as his assistant. Now, he was not as good, certainly not as good as observational astronomer as Brahe was, because when he was a young man, he caught a disease that damaged his eyesight somewhat, and so, when he was a youth, I mean. And so he was not really a gifted observational astronomer himself, but what he was able to do was to find patterns in data. Kepler knew how to use mathematics and to try to massage a regularity out of just massive, copious amounts of data. He became the imperial mathematician, that's, the imperial astronomer, or period astrologer, whatever you want to call him, in 1601. And he took possession of these books. Now, keep in mind, there was some dispute about who actually owned Brahe's observations. Brahe's family sued Kepler to be given possession of these books, but Kepler managed to hold on to them. I think the lawsuit was finally settled something like 20 years later. Fortunately, by that time, Kepler had used these data to great advantage to formulate his three laws. Kepler was interrupted. At one point, he left the imperial court and became provincial mathematician in 1612. His research was interrupted for a while. He had to go home and defend his mother on charges of witchcraft. Despite his defense, she was convicted of witchcraft, but her punishment would just be shown the methods by which she would be tortured in the future if she was ever convicted of witchcraft again. So anyway, he had quite a interesting backstory there, but he was able to take this data from Tycho Brahe and others and combine with some of his own and to come up with three principles that seem to control planetary motion. And when you work on your lab, hopefully you have already started on the take-home lab for this week, which is about Kepler's laws, you will see some of the ways in which he was able to find, say, the orbit of Mars and some other information about the nature of these laws. I'm just going to kind of give you the summary of the first and second law. There's more to it given in the lab that you're doing this week. So here is Kepler's first law. Now, this is probably most important for his willingness to abandon an idea that had been fundamental to models of the heavens since the time of Ptolemy, even before. Everybody thought that things in the heavens were perfect, unchanging, as I said. So what's more perfect than a circle, right? Things in the heavens would move as circles. They wouldn't be so pedestrian as to move in a straight line like things do on the earth, or even a parabola, as Galileo figured out that projectiles do. No, in the heavens, everything has to go in a circle. And Kepler was really the first person to be willing to seriously consider a model that did not have circles as its basis. And that made all the difference. That's what made Kepler's model so much better than any other model of planetary motion before it. So what he said was that the planets move in elliptical orbits. Now, what is an ellipse? Ellipse is one of your conic sections, if you learned about that when you took Algebra 2. The definition of an ellipse, it is a set of points that is a set total distance from two other points called the focuses or foci. So you have 2 points, and those are the foci of your ellipse, and then the total distance from these points to the point on the ellipse is a constant. So if you add this distance and that distance, you get a constant. It is the total, it's all the points that are that total distance from those 2 points. The way you make it is kind of showing you here. You take a string and you attach a string to that point and a string to that, or the other end of the string to that point, and the string has to be kind of loose. And then you just use the string kind of like as a compass, but instead of all going to just one point, the string keeps the total amount of distance from these 2 points to your point on the ellipse constant. And you just kind of move your pencil around like that. Now, this is an ellipse. It is not an oval. People call it oval sometime, and if you say that word, I'm not going to get offended. But I just want you to know, an oval is shaped like this. I didn't do that very well, but that's actually pretty good. An oval is so called because it is shaped like an egg. This is not egg-shaped, and here's why. It has 2 axes of symmetry. This one only has 1 axis of symmetry. It's only symmetric this way. It's not symmetric here. This is a different shape than that. But an ellipse is symmetric on either side of this line and either side of this line. This distance from here to here is called the major axis. This distance from here to here is called the minor axis of that ellipse. So Kepler's first law is that the planets move in ellipses where the sun is at one of these 2 focuses. So the sun is at, like this focus here, and the planet moves in an ellipse around it. So it turns out that this law is just a consequence of the fact that it is a central force. Because we have an inverse square law central force, that's why you're going to get an ellipse as your shape of your path. Inverse square law, we'll talk more about that when we get to Kepler's third law, and we're going to relate it to the law of gravity, so we'll talk more about that tomorrow. But the idea is that any inverse square law, where the force of gravity, or whatever is causing this planet to move around the sun, whatever that force is, if it's an inverse square dependence on the distance away, then you're going to have elliptical orbits. Okay, that's the first law. The second law is a consequence of the conservation of angular momentum. And one of the things I ask you to do in the take-home lab is to relate the conservation of angular momentum to Kepler's second law. So I won't say too much more about that relationship, but let's tell you what the law says. The law says that if you take a line, draw a line from the sun to a planet, and then observe as that planet goes for, say, a certain amount of time. Let us say a month. If you observe that planet for a month and see the area that line that you drew from the sun to the planet sweeps out as the planet moves in its orbit. So over here, the sun swept out an area A1. Over a month, let us say, the line from the sun to the planet swept out this much area. So that much area was covered by that line. If you kept the line connecting the sun to the planet, that is the area that fictional line would sweep out. And then over another month, say from C to D, the line from the sun to the planet would sweep out this much area, A2. And then over a different month, say from E to F, the sun would sweep out that much area. According to Kepler's second law, A1, A2, and A3 are all equal. Now what does that mean? Well, really it means just this. You get closer to the sun and the planet's moving faster. You get farther away from the sun, the planet's moving slower. And that's another concession that Kepler was willing to make that no other astronomer up to his time was willing to do, was to have the planets moving at different speeds at different places in their orbit. Kepler didn't put the planets on little epicycles and have the epicycle center offset from the orbital path to explain why the speed appeared to change. He had the speed change. He said the speed speeds up and slows down. Now we can use this idea to do a problem very simply. If we take certain specific points in the orbit, it's really kind of cool to see how you can do a mathematical problem using conservation of angular momentum. If we just use two particular points in an orbit. For example, let us talk about the perihelion and aphelion. Perihelion means the point of closest approach to the sun for the planet, and aphelion means the point farthest away from the sun for that planet. At those 2 points, as you can tell from this diagram, so if the planet's going around the sun like this, when the planet comes over here, its velocity is this way, and the line from the sun to that point where the planet is this way. They're perpendicular. And also over here, at the aphelion, the planet's going this way, and the line from the sun is this way. So they're perpendicular at those 2 points. Other places, they may not be perpendicular. Okay? Like right over here, looks like the velocity of the planet would be going like this, and then the radius vector is going like that. But at the aphelion and perihelion, the velocity is perpendicular to the radius. So if we say the angular momentum of the planet with the sun at the axis, what is the angular momentum of the planet about the axis that it includes the sun? Well, the formula for angular momentum, the one we talked about, that's not for a rotating object, but just for a moving object. L is equal to R cross P. And so therefore, at that particular point, the magnitude of the angular momentum would be R mv, and the angle is 90 degrees because they're perpendicular at those 2 points, so it's sine 90 degrees, which is 1. And so the angular momentum at point 1, which could be the perihelion, say right here, would just be R1 times mv1. And the angular momentum at point 2, the aphelion, that would just be R2 times m times v2. And of course the mass is the same, so you could cancel out the mass, and you're left with the distance distance from the sun to the planet at perihelion times the speed at perihelion divided by the distance from the sun to the planet at aphelion is equal to the speed at aphelion. So if you know the speed at this point, you can find it at that point. Now, you can use it for any 2 points because angular momentum should be conserved throughout the orbit. Why? Hopefully you just said out loud that the torque, the sun does not exert a torque on the planet because the force vector is going along the radius. The radius vector is going this way and the force vector is going that way. So anywhere on this orbit, the force vector is always going towards the sun. As we're going to talk about, the force of gravity is the central force, right? It goes towards the sun. And the radius vector is going away from the sun. So they're always at 180 degrees, and the sine of 180 degrees is 0. So the sun exerts no torque on the planet as it goes around its orbit, meaning there's no change in angular momentum. So you can use this anywhere. It's just that it's easiest to use this idea in a place where you don't have to worry about what angle the sun, the radius vector from the sun is making with the velocity vector. At those 2 points, the aphelion and perihelion, you know it best. By the way, hopefully you are familiar with those words, apohelion and perihelion. Peri means closest point to, apo or ap means farthest away from. So for example, the perigee and apogee refer to the points in something that is orbiting the Earth. Its closest point would be its perigee, G being the root word then for the Earth, and apogee, farthest away from the Earth. And then all the other planets have a similar term like that. If you talk about Jupiter, for example, it's perijove and apojove and so forth. Now, by the way, these two facts were done by Kepler originally mostly based on the data that he had for the orbit of Mars. That was a problem that he was actually set to work on when he was still working for Tycho Brahe. It was the orbit of Mars that Kepler used, and then later applied to the other planets' orbits as well. But the orbit of Mars was the one that Kepler tried to, after he established what the orbit had to be, had tried to find the shape of that orbit, what geometric figure fit the shape best, and this idea about the area swept out by a line from the sun to the planet along the orbit. He uses data from the orbit of Mars to kind of prove these two ideas, and then he applied to other planets. All right, the third one is the one that we really are going to focus on because it's going to allow us to kind of see how the law of gravity can be supported, Newton's law of gravity can be supported by Kepler's observations. Kepler's third law says this. If you square the period of a planet's orbit, period's time it takes to go around one time in its orbit, right? So it's the year for that planet. If you square the period of a planet and you cube the length of the semi-major axis of the orbit, okay, this is the major axis. It's the long of these two axes. Half of the major axis is the semi-major axis. So if you take that length and cube it, and you take the period of the planet's orbit, its year if you will, and square it, those two quantities will be proportional. And it's a fascinating reading of how Kepler came up with this. He tried all different kinds of ideas. He tried to relate it to music, because Kepler was a great lover of music. And he tried to talk about like the musical intervals, you know, the fourth and the fifth, and the third. All those those musical intervals. He tried to see if they had some relationship to the period, relationship between the period and the major axis. He also, the distancing, the distances that the planets were from each other, he tried to relate that to the known uniform geometric solids, the Platonic solids. You know, they have the tetrahedron and the cube and the dodecahedron, all these shapes, and he tried to see if there was some relationship between those, the radii of those things, their maximum distance from their centers, and their somehow could those things be determining how the distance between the various planets. Never got very far with that, but supposedly he claimed to get this idea. I believe he said he got it in a dream, as I recall correctly, that the relationship between the period of a planet and its semi-major axis. From now on, I'm just going to call this semi-major axis. I'm going to say its radius, even though it's not really a circle necessarily. When we do the math, we're going to probably mostly treat it as circles. We're going to say, well, imagine a planet in a circular orbit. And we can get away with saying that because a lot of them are pretty close to being circular orbit. And a circle, by the way, is an ellipse. A circle is a special case of an ellipse where the two foci are actually the same point. But anyway, what Kepler said, he figured out, is that if you square the period of the planet, and that's proportional to the cube of the radius of the planet from the sun. Let's see if Kepler's right. Here you have, and I asked you to do something like this in the lab, but here you have kind of the results of it. In the lab, I walk you through the process for getting that power, the power, this squared and this cubed. How do you derive at that? Why does it have to be those exact powers? And I'll show you how to do it using logarithm. Here it is, graphing the period squared versus radius cubed for the smaller planets, the inner planets. That's Mercury, Venus, Earth, and Mars. And here I have for the outer planets. Now you could draw them all on one graph, but then you wouldn't be able to see anything about the inner planets because the radii or the semi-major axes of the outer planets are so much larger than those of the inner planets that you wouldn't be able to see anything if you graphed them both. So here, these are the outer planets: Jupiter, Saturn, Uranus, Neptune. Left off Pluto, because Pluto is what we call a dwarf planet. But I'm going to show some of these objects that lie outside of the orbit of Neptune in just a moment here. About that, I don't know if when you have grown up with it, Pluto has always been considered a dwarf planet, at least by some of the international astronomers organizations. But it didn't always used to be. It used to be considered just one of the planets. The problem was they started discovering other things that are just like Pluto outside of the orbit of Neptune. And unless we were going to saddle little kids with the responsibility of learning a mnemonic that has tens or hundreds of planets in it eventually, we had to have some other definition of planet that would keep it manageable. This is not, by the way, the first time in history that the idea of what's a planet has come up. When they first discovered the asteroid belt. The asteroid belt is a collection of asteroids and it's between the orbits of Mars and Jupiter. And when they first discovered, they didn't discover the asteroid belt all at once, they discovered new planets. And for about 20 years, the largest of the asteroids were thought just to be a new planet, or new planets, a couple new planets. They then discovered more and more and more of these asteroids, and they realized, wait a minute, they can't all be planets. So they started calling them asteroids. let me show you some of the other outer planets, the dwarf planets, as it were. Oops, went the wrong way. So there you go. You get to see Pluto on here. Inside, this is what the planet I'm talking about in the asteroid belt series, just to get an idea. And then, because it's a dwarf planet, it's too small to be a planet on its own. And then there's Pluto. Oh, the other thing, it's not too small, because it is round. One of the definitions that some of these astronomers organizations have chosen for a planet is that it has to be large enough to be gravitationally round. In other words, large enough so that its own gravity makes it more or less round. That's why a lot of the asteroids, wouldn't even be considered dwarf planets, because they're not even large enough to do that. Ceres, it turns out, does. It is large enough to do that. However, the other requirement is that it has to clear its own orbit. In other words, it has to be so large enough gravitationally so that as it makes its orbit around, it's attracted the other things that would be in that same orbit. That's kind of controversial too, if you think about it, because even the Earth hasn't really cleared everything out of its orbit. There are near-Earth asteroids, after all. But anyway, enough about that controversy. But I just want to show you that Ceres is on this chart too. And then there's Pluto, and then there's other planets or dwarf planets that have been found outside of the orbit of Pluto. There's Haumea and Makemake and Eris, and I'm sure there's many more by now. I made this graphic several years ago, and I'm sure there's lots of them by now. So you see, they do fit that requirement. They do fit that Kepler's third law. Everything in orbit around the sun is going to fit that same graphic. Here's an example. Let's do one for example. Jupiter is 5.2 astronomical units. An astronomical unit is the distance from the Earth to the sun. The average distance is, I guess, semi-major axis of the Earth. It's convenient to use astronomical units because then you have the Earth as one of your examples, and its orbital radius then, its orbital semi-major axis is 1 AU, and of course the Earth's period is 1 year, and so your constant proportionality in those units is just 1. And you can then easily figure out what the year of another planet is from knowing its distance from the sun. Here's the calculation for Jupiter. So the period of a planet squared should equal some constant times the radius cubed, and that constant turns out it's going to be 1 for the Earth, in terms of the period of the Earth is 1 year squared, and then the radius of the Earth's orbit is 1 AU, that cubed. So if you just use 1, you'll get the period in years if you're using the radius in AU. And so here it is. Calculating it out. This is the constant here, 1 year squared divided by 1 AU cubed, times the radius cubed, which is 5.2 AU cubed, gives you the period of Jupiter squared. You take the square root of that, you end up with 11.9 years. So I have a little quiz for you to do, and the quiz, there's one more of these problems if you want to do it. I didn't put this on the quiz, but so I have a little 5-question quiz if you'd work on that today after you finish watching this video, and then tomorrow we're going to take Kepler's third law and we're going to see how you can associate that with Newton's law of gravity.